Okay, thanks very much for the introduction. I want to present a collaboration of me, that's Rob Forbes from the University of Central Lancashire, and as you heard, I'm seconded part-time to Fujifilm, which is fantastic as an academic to get some exposure to current industry practice. And also I'm grateful for the UK government for funding this innovation scheme that allows me to do that. So whilst I was on my holidays, so to speak, we had the opportunity to explore this technology from Redshift Bio, the Microfluidic Modulation Spectroscopy, and I'm going to tell you a little bit about some of the things we've been doing. So Redshift are the innovator company with this technology, MMS, Microfluidic Modulation Spectroscopy, and that's the heart of the system. I'll talk a little bit more about that. As well as that, they've got an instrument, the AQS3 Pro, that uses that MMS technology, and a very powerful protein analytical software technology, AQS3 Delta, which does, I believe, give some deep insights and is very useful. This instrument's been fairly new, and since 2019 has been adopted by a few companies. So as I say, I'm on secondment. I'm at Billingham and Wilton at Fujifilm and get to spend a bit of time there, and exposure to Fujifilm Diosynth Biotechnologies, who are a major CDMO and have lots of people and lots of technologies and lots of investment, and are well instrumented compared to a university environment that I'm used to. And so they're an end-to-end CDMO looking to partner you from preclinical right through to regulatory approval and launch. In this talk we're going to focus on sort of the formulation early phase stage. So what does a professor do? Well, they have to ask a few questions, and some of the questions that I ask are, do we need any new analytical approaches for biopharmaceutical characterization, and where are we constrained in analytics in formulation? So in other words, is the bulk pharmaceutical substance that produced optimal or compromising in terms of its formulation and delivery properties? And I think there's room for improvement. Some of the thoughts that I had are that we need to be looking at the right area of interest. Do we get the definition, this discriminatory power in that scale of scrutiny to help us to identify key critical quality attributes? Are our methods really good at dealing with the complexity of modern formulations? A lot of analytical methods, you have to use a buffer exchange, or you have to dilute, that can sometimes cause problems. Sometimes in the lifetime of a project, the clinicians get their hands on the material and they say they need a new dose, and you've done all your formulation work at a particular dose. And so then how do you do the comparability? How do you know that changing goalposts, do the analytical methods, are they flexible enough to explore that area? Sometimes we might see things, we might see change, but we don't really know, we haven't really got a full mechanistic insight into why that change is happening. And if we can see change and we have some mechanistic insight, then we've got a chance of managing that change and controlling that change. One of the key problems, key challenges, is time. There's a lot of time pressure. Have we got analytical methods that are predictive of long-term stability and quality? Because we can't afford to wait 2 years to find out that, yes, it's stable. And also we don't have a lot of material, and so have we got some sample sparing technology? So they're the sort of the areas that I think are the challenges, and I was interested in seeing whether this MMS technique addresses any of these challenges and helps us in this space. So this is the instrument, Microfluidic Modulation Spectroscopy. Redshift have got a stand outside, and it's they believe it's the next generation in protein structure determination. And so my question is, how does that fit into this applications for us in these areas? and also in a sort of a biophysical characterization setting in a Fujifilm where there's lots of equipment and lots of work schemes. Does MMS add any value? What does it bring to the table in that space? So that's the context. So the MMS technology provides 5 critical protein quality measurements. It gives us a feeler for aggregation, for quantifying, for stability, for similarity, and for structure. And as you can see here, has a wide range of, can deal with a wide range of concentrations, which is good, and is automated and can deal with complex backgrounds, which is good, which was sort of ticking a few of my sort of constraints. And one of the constraints we have is in the secondary structure. If we're trying to characterize our proteins and monoclonals, we don't have a lot in this secondary structure space. We have circular dichirism, which has concentration constraints and has buffer compatibility challenges. FTIR has been around, but it's quite an onerous workflow, a lot of manipulation, and in its current format has a limited concentration range. So MMS was designed to address the limited opportunities for secondary structure analysis with this automated approach. So it's FTIR. You've all probably had the classes. You know, what's it measuring? It's measuring vibrations. So, and depending upon the environment, you know, alpha helices, beta sheets, we're in different environments. The wave numbers are changed. You know, if we're constrained in a lift, we can't move our arms as much, and so these conformational environments will give us a change in the or changing structures will give us these changes in the vibration. So it's pretty well characterized, and up to now it's not been fully exploited due to the current limitations of infrared measurement technology. So what are those limitations, and why does this system work quite well? What it does is it has 2 arms and a laser, and we have a buffer stream coming in, and we have our sample in the buffer, so that our material of interest is in the buffer. So, and by pumping very fast modulations, we are flipping from the buffer to the sample very, very quickly at high frequency, so we're able to subtract the reference background, and that's giving us a power of precision on the to truly look at the sample in the buffer. Little animation, so it's pumping away, it's sample reference, sample reference, sample reference, sample reference in this microfluidic chip. That gives us our absolute spectrum. So what does it really do? It sort of gives us our differential absorbance. We can get generate the absolute spectrum. That's converted in a second derivative to identify spectral features. We invert it, and then we use deconvolution to get the key secondary structural motifs. So basically, alpha helices, beta sheets, unordered, the relative percentages of those types of structure, giving us that conformational higher order structure. Then the powerful analytics can come into play. Basically 2 sort of streams. We've got a higher order structure analysis, or a stability. Is my sample changing? A similarity sort of assessment. What's changing with the sample? And also this higher order structure percentage, different types of structural motifs. And it has a powerful similarity software where we use this area of overlap or weighted spectral difference to sort of assign a number to how different are the spectra between each other. So here's an example of a reference material, a NIST reference map that shows here in this. We've got so the absolute with concentration, absolute data. The sort of relatively nothing changing much in terms of second derivative. When we convert that into alpha and beta, etc., there's no difference with concentration. That also is correlated with a similarity index, and the software also will give you a calculated concentration, a bit like based on the Beer-Lambert's type approach, where you can get a concentration that's generated just from the structure, just from the data itself, which is good because that's giving you an absolute sort of fit, and you know whether your students, in my case, have done the right dilutions or not. Okay, so that's the basics in a Fujifilm environment where in the early stages Fujifilm are very interested in understanding the protein. Is there a role for this microfluidic modulated spectroscopy? So using a model proprietary to Fuji, a Fuji compound X at 10 milligrams per mil, there's a range of different formulations, different buffers, changing pH, and different additives. And how is my protein behaving in these environments, and what does that tell us about how it's feeling, about life in general? And so this is a sort of a typical type of system that might be used. So using the MMS, what we got is we've got this similarity index, so ranging from about 98 up to 100, and we're also getting generated concentrations just from the spectra alone of 10 mg per mil or thereabouts. So basically our protein X, MAB X in these formulations, just at sort of a first glance, is probably not doing that much exciting. Here we overlay the FTIR MMS spectra. We get a higher order sort of structure for the 10 formulations, and there's nothing absolutely, that clearly stands out. But then using the power of the analytics, if we see at specific wave numbers what is happening for each of the various formulations along the bottom, what we get is that we see that these wave numbers are shifting around a bit. There's a difference at these wave numbers, and we can do this relative stability similarity plot. So formulations E, F and G, they're looking pretty bad in this negative here. Formulations J and K, that's good. They're giving us this positive here that's relating to structural features around the beta and alpha structures. So that on its own is quite interesting. We can get some discriminatory, but how does that, and that's just pure analysis of a sample in these buffers without doing any agitation, stress or whatever, just as is, how is my protein feeling? So we're getting a feeling of, whether it's, if it's stressed or if it's relaxed. And stability is going to be related to, I think, this initial confirmation, and that there's a lot of information in that thing. But how does that relate to other more established techniques? Lots of toys, as I said, at Fuji, lots of ability to do high quality analysis, biophysical characterization. How does it fit in with this kind of sort of workflow? One of the common techniques to assess stability of formulations is differential scanning calorimetry, where you might get an onset temperature, a TM, onset of unfolding, or a midpoint of unfolding. And for the various formulations, the TMs are sort of graded like this: red, bad; green, okay, good. So in terms of correlation of this sort of differential plot from the MMS, how is that relating to when we heat proteins up and get a DSC? Well, what we can see there is that there's a reasonable overlap here, with the greens being okay and the reds being sort of reds. So there's a little bit of overlap there, which is good. When we look at particle content, subvisible particles, which is an indication of aggregation and stability potentially, again we see that we have slightly, in general, higher particles for our higher particle counts for our worst samples that were indicated by MMS, and lower particle counts in general by the MMS as well. So a little bit of a correlation there. In terms of the diffusion interaction parameter by dynamic light scattering, maybe not so good initial sort of correlations with this. DLS, diffusion interaction parameters, can be tricky, but anyway, not so great off the bat correlation. So if we zoom in on 4 of those samples, 4 of those formulations, we're just looking at the effect of pH, going from pH 6 to pH 7.5. So simplifying the structure a little bit and just zooming in on this particular variable. What we see is with change in concentration, we see that increase in size with increasing concentration. So DLS is telling us that potentially our molecules are interacting a bit more with increasing concentration. We're also seeing a general trend that the lower the pH, we see an increase in size as well, or decrease in size as we move towards higher pH. So let's pull up the MMS data, and if we focus on these bands of interest that we know relate to structural motifs, this band here, we're seeing an increase in native structure here, this way, and we're seeing a decrease in misfolded structure this way. So effectively we're seeing an increase in native structure and a decrease in misfolded structure, and that's correlating with the pH. So the higher pH is behaving better, and that's telling us something about structurally that that's why it's behaving better at higher pH. We've got higher native structure and a decrease in misfolded structure. So now, if we now look at that data in this armory of other analytical techniques we've got, we can see that the trends are starting to look a little bit more realistic. We're seeing a trend of increasing TM with increasing pH, a trend in decreasing subvisible particles with increasing pH, and a trend in the interaction parameter being less negative, all pointing to less sort of tendency to sort of aggregate, and we've got this direct structural readout from the MMS telling us what's happening at a structural level, as well as these direct sort of measurements from these other biophysical characterization methods. And we know that that trend that we saw, that deviation, is real, because from a previous study pressure-induced aggregates were added, so they were doped into a system, so we were seeing an increase in native structure and a decrease in misfolded structure with larger amounts of, or decreasing amounts of aggregates. So those trends are sort of backed up and are real. So in an early formulation summary, does MMS fit in nicely? And I think it adds some value. There was a reasonable correlation with MMS and other techniques, particularly on the correlation was good when we just zoomed in on pH, and it can cope with natural formulations and complex environments. So if we address my initial sort of areas of interest, where do I think MMS adds value? I think that powerful software does give us a scale of scrutiny that's a sort of a next level, gives us that differentiating power. It can deal with complexity. We've got no need to do any dilution. You might run DSC at 1 mg per mil, for example. You can run this at relevant concentrations. Because it can cope with that change, it gives you that less worrying about changing goalposts to explore perhaps new buffers or new concentrations that might be required from your project managers. Because we're correlating those structural features with beta sheets that are intramolecular species, that gives us some provision of mechanism of insight. And so it has potential in predictive of long-term stability, quality. At the moment, it's not particularly sample sparing, but I understand that Redshift are looking at to make it less sample, to be more sample sparing, so you get the same level of information with less material. And with that, I'd like to thank the UK for my secondment scholarship and people at Fujifilm for the data generation. Thank you for your interest. I'm welcome to take any questions.
Any questions? Yeah, thank you, that was really interesting. I was wondering, the sample that you inject, is it in one buffer and then the sample injection system changes it into the formulations? Or do you have to have
you have to make up your, whatever you might think is your range of, you explore different buffers, you might explore different concentrations, you need to have a match sort of reference. You know, you need to have you could dialyze the proteins in whatever it's in, and then you've got a reference buffer coming along, and so you're subtracting that buffer system, and that means you can zoom in on the features of your protein. So you do have to make up your own. And actually, sorry, it's a 96 well plate format. There's a video at the so it's automated. You can 96 well plate format.
So that means you have to then have 10 different buffers as well that are injected for the analysis?
Yeah, you've got, if you're making up the different formulations, you would probably have some buffer if you're making it up into those different formulations, yeah.
Okay, no, I was just thinking about how much sample you would need and how easy it is to...
You need about, I think, for really good, I mean, a mg per mil is seen as really good, and I think you need a milliliter. It's quite, at the moment, it's quite a high volume, it's over a milliliter, because it's collecting so many data points to get that level of discriminatory power. Thank you.
Hi, lovely presentation, thank you. I was wondering how your data then, did you do any stability data at 6 months, 25 degrees, and how did they then compare? That's what we need to do, yes. But it's, you know, the world of biopharmaceutical development is that you don't make 20 potential formulations, put them all on storage, wait 2 years and then pick one. You have to pick one or two, you know, you have to pick without knowing the full stability data in advance. But that is the study that needs to be done, that we would put longer term stability. I'm going to be at Fuji for a bit longer, so maybe I can get them to do some stability studies on different formulations, so that long-term stability is you know, to explore that. Yeah, so that's why I didn't give it a bold. We're sort of nearly there. We're on the way, but it's not delivered at the moment.
Okay.
Thank you very much.
Thank you very much.